All right, let's jump in. So, I realized that eight was due last Wednesday, but there was two things at the end, the organic nomenclature, whatever I want to emphasize, and so I'll draw some of those things for you this morning, and then we'll get into the things that are due Monday. Okay. So these are some of the structures that they were asking you to draw. I put a few extras on here, so I just wanted to get you to practice drawing these. You did these in Alex, is that right? Some of these, yeah. Were they tricky? Did you? They were these. Okay.
Listen, once you had like an idea, like once you did one of them, it made sense.
Okay.
If you didn't, it didn't.
Okay, so hopefully if it didn't make sense, then after this, it'll make some more sense. Okay, so let's jump in. So for me as a chemist, I see some of these words and I recognize them. Like I know acetylene is this. And this is one of the things for organic. Once you start getting familiar with molecules, you're going to just memorize certain things, and it's kind of like going through the woods. The first time you go on a trail or through the woods, you don't recognize anything. Okay, and it's easy to get lost. You keep going back and forth, you start recognizing certain trees, you start recognizing certain paths or routes or whatever, and that's the way learning a new subject is. Eventually, you start recognizing things. And it makes life easier. So if this is acetylene, then chloroacetylene, I just take off one of those hydrogens and put a chlorine there. Okay. Same with the aldehydes and amines and so on. So, but let's start from scratch. So if I'm looking at this molecule, if I'm going to do a Lewis dot structure for this molecule, I'm going to hold the hydrogens off to the end. Okay. So let's quickly count the valence electrons. I've got 2 times 4 for the carbon, okay? 2 times 4, plus 1 for the hydrogen, plus 7 for the chlorine. Okay, so that looks like 16. Okay, so I'm gonna bond all the heavy atoms together first. So I'm gonna say a carbon, and a chlorine. Aside from those like chlorooxyanions, chlorine is always something that just bonds to one thing. It just makes one bond in the Lewis dot structures, unless it's like ClO3, ClO4. That's when chlorine's in the middle and you got oxygens all around it. But like HCl, you got the chlorine stuck on a hydrogen. Carbon tetrachloride, you got 4 chlorines stuck on there, but each chlorine just has one bond. Because the chlorine, if you were to look at its Lewis dot structure, it's Cl and it's 1, 2, 3, 4, 5, 6, 7. So it's got that one open spot. So it's really just going to click with one thing, unless it gets attacked by oxygen. Okay, but for most time, chlorine is just going to stick on. And so what I'm trying to justify is that the chlorine's not in the middle; it's bonded on the end. So you got 2 carbons connected to each other and a chlorine snapped on the end. So I've used up 4 electrons in the bonding. Okay. So I've got 12 left. So we'll put them on the most electronegative atom first. 1, 2, 3, 4, 5, 6. All right. And so used up 6. Okay. And I've got 6 left. And I've also got this hydrogen I need to stick on there. So I'm just going to stick the hydrogen on the end here. That uses up another 2. Okay, so I've got 4 left. And so I can put them on the carbons. There's no reason to pick one and, give it all 4. I'll put 2 on this one and 2 on that one. So I've used up all my valence electrons. And then what's the next step? Octet rule. So we look at this. And so, again, it doesn't apply to hydrogen. Hydrogen just wants to be like helium, and helium has 2 electrons. So hydrogen's happy. But the chlorine, it can claim 8 in terms of the octet rule counting, and so it's happy. But these carbons are not so happy. 2, 4, 6. It can only claim 6, and so it's going to want these electrons to drop in there and form a double bond. And this one only has 6, so it's going to want these to drop in and form a triple bond. And so this is what we end up with. So that's chloroacetylene. And it's very similar to what I said. If acetylene is, HC, triple bond to C, and another H, you take the H off and put a chloro on there, you have chloroacetylene. Okay, what about acetaldehyde? So again, all of these are 2-carbon molecules. And so they're going to be the carbons are going to be bonded together with some other elements stuck to them. So let's go ahead and just try to do this without counting up all the electrons. So we've got, okay, so there's our heavy atoms connected to each other, and we've got 4 hydrogens. Okay, so let's put 3 on here and 1 here, and we're out of hydrogens. There's our 4 hydrogens, and we've got, let's go ahead, let's count our valence electrons. Let's do that. So we had 2 times 4 for the carbon, plus 4 for the hydrogens, plus 6 for the oxygen. So that's 10, 18. Okay, so we've used up 2, 4, 6, 8, 10, 12. Okay, we've got 6 left. So we can go 1, 2, 3, 4, 5, 6. Let's put all 6 on the oxygen. Why would we do that? Why wouldn't we put 2 on the carbon? It's the electronegativity thing. So we put them on the most electronegative atom until it has an octet. So we got oxygen all happy there. Minus 6, we got 0. Okay, so now we're looking at this molecule. This carbon does not have an octet, so it's going to want to share these electrons with the oxygen. So we would form a double bond and scratch those guys out. And that's acetaldehyde. Let's do ethylamine. CCN. Okay. It's got 7 hydrogens. So we'll put 3 here, because every carbon wants to have 4 bonds. 4 bonds equals 8 electrons, and so that carbon's happy. Okay, we'll put 2 here. All right. And that's 5. We need 2 more, so we'll put 2 here. Okay. If we were to add up the total valence electrons, we've got 2 times 4 plus 7 plus 5 for the nitrogen. Okay. 7 goes right there. 7 and 5 is 12. Plus 8, that's going to be 20. So let's add them up. All the bonds count for 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've got 2 more left, and that's going to be this double bond, or lone pair on the nitrogen. So there's our 20 electrons. So that would be ethylamine. And what you're going to notice is some of these things are standard groups. Like this right here is the aldehyde. This carbon double bond to oxygen with 2 lone pairs, and then the hydrogen on that carbon. So that's what we mean by an aldehyde group, this aldehyde piece. And acet is like acetic acid. Acetic acid has 2 carbons, and so a lot of these 2 carbon molecules have this root ACET, like acetylene, acetaldehyde. We could have called this acetylamine probably. We could call this acid alcohol, but ethyl is the more proper name. Ethyl means 2 carbons. So let's do ethyl alcohol. CCO is the backbone of that molecule. We've got 6 hydrogens. So we'll put 3 here on the end, 2 on the one in the middle, and that's only 5. So we've got 1 more, so we'll stick it on the oxygen. if we were to add up all of those valence electrons that we have, we still have 4 left over, and those are going to go on the oxygen. So this kind of looks like water, right? But on this side, we've taken off a hydrogen, we put this organic-y piece on there, and so we've made an alcohol. So all of the alcohols have this OH piece. So this piece right here, when it's hooked to an organic molecule, is called an alcohol. And this piece right here, I didn't label it, but this piece right here is the amine. So I really liked that Alex was sort of pushing you into organic molecules, organic naming. Okay. Now this last one is a little strange. It's got this term vinyl. How many people have heard of vinyl before? Yeah. Where did you hear? What is vinyl? The record. What is the vinyl part of a record? It's the polymer, the plastic polymer that it's made out of. Okay. Yes. So when we have those electrons left over, we make single bonds first, and when we have electrons left over, they go to the atoms that are closest to this corner. So fluorine wants the electrons the most, and then oxygen wants them really bad too. So we could put them on the carbon, or we could put them on the oxygen, and oxygen's more close to this corner. So that term is electronegativity, meaning they want electrons. The real science behind it is that they have more protons. Okay, so the protons are sucking those electrons towards them. So we put those electrons on the oxygen or the chlorine or the nitrogen before we put them on the carbon. If we still have some after we've filled up the valence of oxygen or fluorine or chlorine, then we can put them on the carbon like we did for acetylene. And then the carbons didn't have octets, so we made the triple bond. So that's the last step. So vinyl is a molecule that was used to make polymers. So this is going to be the monomer, the single molecule that is polymerized to make the polymer that we know as vinyl. Okay. So vinyl alcohol. So what's going to happen is we're not going to have enough hydrogens, and we're going to have to make double bonds. So let's go ahead and make our backbone. Okay, and let's put our hydrogens on there. Just because I know how this is going to go, I'm going to go ahead and just, I'm not going to put all 3 on this carbon. I'm going to put hydrogen there, hydrogen there, hydrogen here. And this says it's an alcohol. What does that tell me? Where do I put this last hydrogen? I'm about to put the 4th hydrogen on there. Where do I need to put it? On the oxygen, because it says it's an alcohol. So it's got to go over here. Let's add up our valence electrons for this one. So 2 times 4 for the carbons, plus 4 for the hydrogens, plus 6. Okay, so 6 and 4 is 10, plus another 8, so 18. All right, we've used up 2, 4, 6, 8, 10, 12. Okay, so that's going to be 6 left over. So I put them on oxygen first. That's what we were talking about just 5 seconds ago. Okay, so they go on oxygen first. I've used up 4 of them. I've got 2 more. So I'll put them on this carbon right there. So that we would be done, but we don't have an octet on the carbon. So this one is short. It's got 6 electrons. This one's happy. It's got 8. But we're going to share these 2 right there and make a double bond. So I'm going to put that mark there, and I'm going to scratch this out. So that's vinyl alcohol. Now, what makes it polymerizable is that double bond. So we can put it in, there's several different ways to make polymers. We teach a whole course on polymerization. Okay, but you can get 2 of these molecules close together, and that double bond can hop over to another molecule like a chain reaction, and it'll snap to that one, and then its double bond will snap to another one, and it'll snap to another one, and so on. And this can happen in a material. In fact, it can happen in a material and cause a release of a lot of heat and can explode. So sometimes polymer plants will have explosions. They'll have polymerization happen in their pipes, and then they'll have a pipe that bursts because it releases way too much heat. But this is something that we use to make all of the plastic that you see around you, okay, and all the microplastics that you have in you. That's not so good. Okay, so these are some common organic structure names. So already we had some of these in this molecule, like these right here, the CH3 piece. This is a methyl. See that CH3? Methyl. Okay, this is a CH2 piece. That's called a methyl ENE, methylene. So we see these in molecules all the time. So this is just a very common organic structure building block. Is the end of a lot of molecules has this CH3 piece. So it's it continues on bonding to something else, but this is an end group that sticks on the end, and it's got a CH3. That carbon's bonded to 4 things. It's very happy. This one is in the between. So like you might have a chain where it's in between. And now, so a nice little syllogism that people are lazy and scientists are people. Therefore, scientists are lazy, okay? And we get so tired of drawing all of our H's that we just omit them. And we just assume if you see a line there, and we don't even draw the carbons. So this is the way an organic chemist would draw this molecule. This zigzaggy line has a carbon here, and a carbon there, and a carbon there, and we're not even showing the hydrogens. They're just showing the important stuff. The CHs don't really react very much. So in this molecule, the reactive stuff is this hydroxy group. So this is a hydroxy. And they don't show the lone pairs, but there should be 2 lone pairs on that oxygen. And then this is an acid group, an organic acid. You can't read my handwriting. Okay. And it also, they're omitting the lone pairs, but they see that double bond piece. I mean, this is just such a common thing in organic chemistry and all these organic molecules that we don't draw the CHs. We don't even label the Cs. We just draw these lines, and all those lines, everywhere there's a vertex or this sharp bend, there's a carbon there. There's even a carbon right here too. So this has 4 carbons in it. Let me give you some breakdown here. So methyl, so METH equals 1 carbon. Ethyl equals 2. Prop equals 3. And there's a table of this in the book, but I want to get down to but, B-U-T, equals 4. And so this is gamma, which here's this acid group, and we can use Greek characters sometimes to keep track of things. We have the alpha carbon next to the acid group, the beta carbon, the gamma carbon. And on the gamma carbon, we have a hydroxy. So it's gamma hydroxy. So there's our hydroxy group. Butyric, so B-U-T, means there's 4 carbons. And then acid, that's the acid group. So this is how all of the organic molecules are put together by these common organic names and structures. So that's organic 1. You're going to learn a lot about that if you go on to organic 1. I just would like for you to recognize these kinds of things, like an amine, like a hydroxy or an alcohol, because if you're looking up here and you see ethyl alcohol and you see this right here, notice there's no OH in that formula. Like, how would you know there's an OH? You have to know it from the name. If they tell you it's an alcohol, then you've got this piece right here on the end of the molecule somewhere. Okay.
What's DFSA stand for?
Oh, drug facilitated sexual assault. Yeah, so for forensics applications. That's why that little gray box is titled forensic application. So this is a organic molecule. It's also really a kind of a pernicious one because our body makes this naturally. So everybody has a certain amount of it in their body. And so if somebody were to slip something in someone's drink and it like really, like one little capful is like drinking a whole 6-pack. It has that dramatic of an effect. And so somebody could be really incapacitated, sexually assaulted, and then this is a natural compound in our body, so we pee it out really quickly. And so if they wait too long to go get a blood test or some sort of analysis, then they can't show that they had this in their body, right? Because you pee it out real fast. And so it's really hard to detect GHB in the body after a day or two. I don't exactly know the timeline, but it comes out very quickly. So this is one of the ones that you want to be aware of. Don't let anybody ever mess with your drink, right? And always, be with a friend so they can watch if you go to the restroom or something like that. But this is the molecule that you might hear about, GHB, gamma hydroxybutyric acid. And also we had a speaker a few years ago, she and her brother were big partiers at college, and they had a bottle of GHB, and they were all taking capfuls of it to kind of get a super fast buzz and everything. And her brother took a big old chug of it and died. So it was a central nervous system depressant, means it slows your heart rate down, slows your breathing down, and he just quit breathing. Yeah, and so she felt obviously devastated by this. And so she kind of made it her mission to go around to campuses and talk about this, not to do this, to get people aware of it. A carbonyl. Okay, so let's look at a carbonyl before we run out of time. This is a carbon double bonded to an oxygen and bonded to something else. So a lot of times organic chemists will use R just to represent any other part of the molecule. Other stuff. Okay. So we use these, they're called R groups, but this right here is the carbonyl in the middle. And you can see that the acid group has a carbonyl and a hydroxy connected to each other, and it makes its own thing, an acid, but the carbonyl can just be between other stuff, and that would be a carbonyl. We've seen an amine already, the NH2 group, with the lone pairs on the nitrogen. So those are some organic structures, and you guys had to do a few of those in ALEX. It's just kind of dip your toes into the deeper end to prepare those people that are going to go on. Okay, so let's look now at the electron groups and the 3D shapes of molecules. So we're dealing with this valence shell electron pair repulsion theory, and it's part of the name, but it's not always a pair of electrons. It really should be electron groups or electron domains. We also call it VSEPR theory because it's easier to pronounce than VSEPR theory. Okay, so when you hear me say VSEPR theory, I'm really talking about VSEPR, VSEPR. And it's the electron groups that repel each other and adopt a geometry of maximum distance around each atom. So the way we do this is we make the Lewis dot structure. So this is a part of the course where it builds. If you're no good at making Lewis dot structures, you're going to stink at this. So you got to get good at Lewis dot structures before you can be good at 3D shapes. So we make that. We do the double or triple bonds for carbon, nitrogen, and oxygen. And then we analyze those groups around the central atom, and we maximize the distance between those groups using 3 dimensions too. So not everything's stuck in a plane. So here are the geometries of maximum distance. If you've got 2 domains, they're going to get as far apart from each other, so it's going to be a linear structure. If you have 3, you're going to have 120 degrees. Okay, that makes sense. Around a circle, 1/3 of the circle is 120 degrees all the way around. And then 4th, you're not going to be stuck at 90 degrees because we have the 3rd dimension that we can go in. And so instead of staying at 90 degree angles, they're going to snap to 109 degrees, 109.5 to make a tetrahedral structure. And then if we put a 5th one on there, then you form like the trigonal planar part around the middle, and then you have one at each pole. So this is like the equator around the middle, and those are the poles. And then if you put 6 together, we have an octahedral. So these are the 6 basic structures around all the different atoms. And I don't remember back, I showed Gaussian and I showed the periodic table, and you can click on an atom and you got all the different atom types at the bottom. They were these 6 structures. So in Gaussian, you can pick which one you want and you can build your molecule accordingly. But what we're doing is we're taking a Lewis dot structure and then we're seeing which one of these it snaps to. So let's go through these. And you can practice with all of these in your notes. Let's just draw BH2. That'll be the simplest one. So beryllium is over here. It's got 2 valence electrons. Each hydrogen brings 1. So we've got H, Be, H. And so that's going to be a linear molecule. You got 180 degrees between the 2 bonds. That one's easy. Let's do some more difficult ones. Otherwise, we'll run out of time. Okay, let's do BH3. So boron has 3 valence electrons, and the hydrogens each have 1. So we have enough to make a single bond between each of those. So we have a H. I'll draw it wrong first. Okay, this is how you might draw it. Just it's like I call this the freshman structure, and then we go to the VSEPR shape. So these are 90 degrees. And this is 180, which doesn't really work, does it? Okay, because those 90 degrees are going to get further apart, and it's going to finally snap down here to this trigonal planar where you have an H on each end and the boron in the middle. So that's the trigonal planar structure. But we don't always have atoms at the ends of those things. Let's do ozone. So the Lewis dot structure for ozone, can go back and you can look to see how we drew this. I'm cutting to the chase so that we can finish. Okay. And then we have 2 here. Okay, so that's ozone. And we've drawn it linearly, but how many electron domains do we have? We've got to count up these electron domains. And so this one has 1 here, 1 there, and 1 there. So 3 domains, 3 electron groups, if you want to think of it that way. Alex calls them groups. So it's electron pair repulsion theory, but this isn't a pair right here, right? It's a double bond, but we count that as 1 group. So it really should be electron group repulsion theory or something like that. But it is what it is. So we're gonna split this around. Again, this trigonal planar structure, we're gonna have an oxygen in the middle. And this one down here with the double bond. And then this lone pair is gonna take up one of those spots. So this is 120 degrees here, and this is 120 degrees. Does everybody see how that works? Okay. Now, this molecule with the BH3, we would call that trigonal planar. So that would be the molecular structure name. This one right here has a trigonal planar electronic structure. And these are my terms that I emphasize, because there's a difference between the structure of the electron cloud and where the atoms are. So look at the atoms. These atoms are in a bent molecular structure. And that's why I've color-coded these. See, there's a difference between a molecular structure and an electronic structure. So if you've got 3 atoms, they can be linear or they can be bent. Okay. And in this case for ozone, it's a bent molecular structure. So in a lot of the ALEX ones, you got a little drop-down box that says which label accurately describes this structure. And the electron cloud is trigonal planar, but the molecular structure is bent. So you would go down the drop-down box and pick bent on that. Bent, yeah. You're smiling, was it? Did you? You see what?
I just see a cute little face right there.
Oh, this little smile. Yeah. And his arms are like, yeah. Okay, very good. Yep.
So does that happen for almost all?
Yeah. And so this one here, this one really isn't going to have a good name, but we still see the same kind of thing for this carbon. So this is formaldehyde. We've drawn the Lewis dot structure for formaldehyde before. It's a carbonyl. It's the simplest carbonyl because it just has hydrogens as R groups. So the extra stuff around the carbonyl is just 2 hydrogens. And again, the initial guess, or the best guess for this, is 120 degrees around all of these angles. It might be a little different. There's all that electron cloud stuff around the carbonyl, and so it might push the hydrogens down a little bit, but who knows, it might pull them up. You know, you'd have to actually do a calculation to figure out which way it does. But again, around that carbon atom, so just this piece right here is a trigonal planar electronic structure, okay, just around that carbon. But it's the structure of the electron cloud around that carbon. Okay, let's look at tetrahedral ones. Methane's the easiest. Okay, so if we were to draw the methane Lewis dot structure, we would get this, and it looks planar. But then when we allow those hydrogens to move in 3 dimensions to get as far apart from each other, we get this tetrahedron. And so this, we would put a hydrogen at each of the ends of those sticks, those 4 bonds, and we'd have the carbon in the middle. Now that's meant to be a 3D looking shape, and it's hard to draw 3D stuff on a 2D surface. So we use wedges and dashes. So like if you're looking down a highway, you know, it's really fat where you're standing, and it gets thinner as it goes further and further into the distance. Okay. And then if you're going back into the plane of the board, we draw dashes to kind of show that it's behind the board. And so again, we would draw the wide dash closest to us and the smallest dash farther away. So we could draw this carbon, this methane molecule, this CH4, like this. And I want to take issue with ALEX a little bit, and I'll show you why in a second. These hydrogens are, if we were to look at that molecule from the side, these hydrogens would be very close to each other. They'd be right in front of each other and behind each other. So the wedge is coming out, that's the hydrogen coming out, and the other hydrogen is going back into behind the board. And so from your perspective, they're in front of, one's in front of the other. And so the wedges and dashes have to be drawn close to each other. This is what ALEX is doing, and it's messing you up because when you get to my PChem class, the way you draw these is very important. Notice you need to be able to see the 3-fold symmetry in that molecule. I could snap this molecule 1/3 of a turn, and it would look the same, right? I can see that it's 1, 2, 3. It's like, three hydrogens that can snap as I spin that molecule. ALEX is doing this. ALEX is taking this drawing, which looks like 90 degrees, and just doing a wedge here and a dash there. And that's garbage. Okay, because it's misleading. I can't look at that and see 3-fold symmetry. And in PChem, we're going to need you to see 3-fold symmetry and 4-fold symmetry and all of that. So draw your molecules like this. Whenever you have wedges and dashes, those wedges and dashed atoms, I need to be very close to each other. Let's do ammonia. We've done the Lewis dot structure for ammonia in class before, so this is what it would look like. NH3. So look how close my wedges and dashes are. So we're showing those hydrogens in front of each other. In fact, it looks just like this molecule, only we've taken this hydrogen away and replaced it with a lone pair, right? Because it's the same tetrahedral base, the tetrahedral electronic structure, and we're just putting different atoms in that electronic structure, okay? So this has the nitrogen and 3 hydrogens, and it's not a tetrahedral molecular structure. The molecular structure here would be a trigonal pyramid. It's a pyramid, right? It's a a triangular volumetric shape, but it's got 3 atoms at the base. What do they call it? A square pyramid would have 4 at the base. So
all pyramids gonna have like a lone pair at the top of the central atom.
I don't think so, because you could have like if we put chlorines here, okay, and a hydrogen on top, it'd kind of be more like a pyramid than a tetrahedron, because the hydrogen's not the same as the chlorines. And so I would call that one a trigonal pyramid too. Yeah. But the electronic structure is tetrahedral for all of these. When you have a carbon with four groups around it, we're talking about electronic structure is a tetrahedral thing, but you have different atoms at the ends of those groups, and then you use the atoms to name the molecule. So the atomic positions name the molecule, like trigonal pyramid. Let's look at water. So drawing the same kind of structure for water, we would maybe draw the O, the H up, maybe the H over here, and then we don't need any wedges and dashes because we've got the 2 lone pairs, but they're kind of one in front of the other. Okay, but you see it's still that same tetrahedral electronic structure, but this molecule is labeled bent. Again, it's 3 atoms that are not in a line. If they're in a line, it's linear. If they're not in a line, it's bent. So it's pretty straightforward. Use the atoms to name the molecular structure. You can write that down. Use the atoms to name the molecular structure. But you use the electron groups to know the angles between them. Because in all of these cases, these are all 109.5 degree angles. At least it's a good start. It's a good guess. Okay. Let's keep going. We got anything. The tetrahedron one is really important because that's so common. All of the organic molecules, we could build that hydroxybutyric acid. We had the HO here. Then we had this. We had the carbon, a carbon, a carbon. Yeah, the 4th one, carbon. We had the carbonyl and the OH for the acid group. So here's the Lewis dot structure for GHB. And what about these hydrogens? All those carbon-carbon bonds are in the plane of the paper. So what about this carbon? It's supposed to have 4 things bonded to it. So I would have a wedge hydrogen and a dashed hydrogen. And a wedge hydrogen. Can I get you to close that door for me? So do you see how now the 3D shape of this molecule has those wedges and dashed hydrogens that come out of the board and go behind the board. So they're like these little fingers like that. Okay. And it's just bristling with those things. And so again, we're lazy, so we don't even draw them. We just draw the zigzag because it's tedious. CH2, CH2, CH2. That's not the important part of the molecule. The OH is, the acid is. So we just eliminate them. But they're there, and that's how you would draw the molecule. So now what are the angles here? Let's look at all the angles in this molecule. We're drawing here. I'm getting too excited. This angle right here, what angle would you predict right there? There's 4 domains or groups around that carbon, and so that's this one, 109.5. Sounds like a radio station. But what about this over here, this acid group? What about this angle right here?
120.
Yeah, you did that fast. How did you know?
There's
3 electron groups around that carbon. And 1/3 of a turn is 120 degrees. So that's 120. And we're not showing the whole shape here. We just put an OH. We could draw a bond there, but what is that one going to be? So yeah, so these non-bonded pairs give us four groups. Yeah, so 109.5 here. Y'all are going to be so good at this. Yeah, so and your peers are going to be going, I never learned that. So you write me a nice thank you note later after you get out of the class. Okay, so then trigonal planar electronic structure. Here's a very classic molecule for this one. No, that's actually trigonal bipyramidal, so that's a copy paste error. Trigonal bipyramidal. Okay. So this, whenever it has 5 groups in it, so we had the P, I'm just draw it on here, the phosphorus in the middle, and the chlorines all the way around. So we have 5 of them. So do you see how that works? Now, how do we draw this one? There's a couple of ways to draw this one. We can have the phosphorus in the middle. We do the poles. So there's the 2 poles, the chlorides. We know they're going to have 3 pairs of electrons. And then we're going to have one that comes out. Notice I'm drawing those lines not as wedges or dashes. We're going to do that next. So these 3 bonds are in the plane of the paper. Everybody, even in the back, you understand that like the plane of the paper, you just draw those straight lines. The wedges and dashes are for the things that come out of the front of the paper or behind the paper. The wedges bring it up front, the dashes take it back behind. And so we'll draw a dashed one for the chlorine that's in the back here, Cl. And then we'll draw a wedge for the one that's in the front. And we'll draw those pretty close together. So that's what makes that triangle around the equator. So they look really close to each other, but that angle between those is 120 degrees. And the angle here is 120 degrees. And the angle in the back is 120. And then from the equator to the pole, that's 90 degrees. Okay, and from pole to pole all the way around is 180, as you might imagine. Now, if we do the BrCl3, we did this one earlier when we were working on Lewis dot structures. Let me just draw this one real quick. BrCl, we have 2 poles and 1 at the equator. And then we have 4 more electrons to fill out. And so they go here in the other 2 equatorial positions. So electronically, this is trigonal bipyramid. All of these electronically have 5 domains or 5 groups of electrons, so they're trigonal bipyramid. But this one is called T-shaped. A T-shaped molecular structure. I've drawn it sideways, but you can look at that and you can see the T. Okay, where the chlorines are. So we're using the positions of the atoms to name the molecular structure. Okay. SF4 is going to be square planar. So you have the S in the middle, and you end up with, I'm going to draw the wedges and dashes. F, F. And then up top, we've got a lone pair, and down below, we've got a lone pair. So it ends up being a square planar molecule. Last one, this octahedron. So here we have, oh, wait a second. Yeah, I did. I got too carried away. Yeah, this one only has, let's see. Is this one may not be square planar, maybe square pyramid. Yeah, that's right. So, yeah, so I only have 5 electron domains. Oof. Let me skip that one. I'll research it to make sure. It may be one of the ones in Alex, but I don't want to mislead you. Okay, let's do the octahedra before we run out of time. SF6 is the classic example. When I get in a hurry, I do a squiggly line. Okay. Now, if you see there's 6 points on that structure where we put the atoms, and this is another copy paste error here. So this is the octahedral electronic structure, and this is an octahedral molecular structure. But where's the octa part? Okay, this is called an octahedral, but there's 6 atoms around a central atom. And the thing that is 8 about this structure is there are 8 triangular faces on it. So if you look at an octahedral dice, you might have an 8-sided dice. It's an octahedral dice because the faces, there's 8 of those faces. So there's only 6 vertices, but there's 8 faces. Okay, so that, don't be confused by that. Yeah. So, and then you can do, this was the xenon one that I just did. So xenon tetrafluoride would have the fluorines here around the middle. And the 2 lone pairs on top and bottom. And we use the locations of the atoms to name the structure, so that's a square planar one. So I think I've gone through all, I mean, maybe not every one of the odd shapes. This one's going to have a lone pair. I think this one's going to be a... I think this one's a square pyramid. So what you would have is you would have a fluorine on 5 of these spots and a lone pair on the last one, on the 6th one. And so then a lone pair down here. And so then it's this square pyramid as opposed to the trigonal pyramid. So I wanted to have an example of each of those. So there's your VSEPR shapes, and the difference between, the main thing, the difference between electronic structure, which is how many groups you have of electrons, and where the atoms go. The atoms name the molecular structure. So you could have bent and T-shaped and square planar and so on. And here's the whole diagram of all of them. So you've got all these different things, and that's good. All right, see you next time. I will be here Monday. I just won't be here on Wednesday. Yeah. Okay.